So, hello everyone, and today I would like to talk about Bernoulli's equation. Now, simply, Bernoulli's equation is the general form of it is dy over dx plus with a function in terms of x times with y, which is the dependent variable for this case, is equal to q of x times with y raised to the power of n. And we put the condition of n cannot be 0 and cannot be 1. This is because that, let's say n is 0, then we can solve this by using the integrating factor, and from there you could solve it because it's a linear differential equation, first order linear differential equation. But if n is equal to 1, well, you can solve it using separable variables which you collect in terms of y left hand side and in terms of x on the right hand side. But Bernoulli's equation is a bit different. I believe that it is from Jacob Bernoulli. Is that what happens if n is not 0, 1? Now, the way we want to solve this is by using substitution, and it's a very specific substitution. And this substitution helps us to convert the Bernoulli's equation to a first order linear differential equation, if I'm not mistaken. And then the final result, we will re-substitute the substitution, and then from there we obtain the results. But we solve the question anyway. So I would like to show you, it's not proof, it's just basically I am expressing Bernoulli's equation to the first order linear differential equation. So yeah, as I said previously, we will be using substitution. So u is equal to y raised to the power of 1 minus n. Okay, now after this we have to take the first derivative. So in respect of x, therefore it will be du is equal to 1 minus n. I believe this will be y raised to the power of negative n dy. Okay, and now for the next line I want to rearrange the terms. So this would be 1 divided by 1 minus n, and then du is equal to y raised to the power of negative n dy. Alright, so the question here is that how are we going to substitute into our differential equation? Now, first things first is that based on our differential equation here, we have to divide both sides with y raised to the power of n. And by doing so, we will obtain the following. So when we divide both sides with y raised to the power of n, it means that we are multiplying both sides with 1 over y to the power of n. So by using the index laws, we will obtain y by multiplying both sides with y raised to the power of negative n. I think this implies that n is a positive integer. I'm not sure. I can't clarify about what are the properties of n. But anyway, yeah. So okay. So by multiplying both sides with y raised to the power of negative n. So I'm gonna write down first to give you a really good idea of what am I going to do. And after this, let's try and solve an example. Okay, but I'll not be deriving this. Well, I mean, I will. I mean, I have to. Just to determine the substitution, the proper substitution. So here we go. And from here, when we expand, first things first, this one will be y to the power of negative n dy over dx. And then plus p of x. And we know that y raised to the power of negative n times y. So basically we will be applying the index laws. So it will be y raised to the power of 1 minus n is equal to and y raised to the power negative n times y raised to the power of n. We can cancel out one another, so we are left with q of x. Okay. So what is the next term? So basically, the terms that we have here, the first and second term, we will be substituting it Therefore, we will obtain the first order linear differential equation, and we will be using the techniques that we know how to solve, integrating factor, etc. So from here, um, we could we know this is similar to this term. Therefore, we can substitute to become 1 over 1 minus n du over dx plus p of x. This is similar to this term, so you obtain p of x times u is equal to q of x. And as you can see here, this is it's very similar to the first order linear differential equation which we learned before, and we can solve this factor sorry, integrating factor. So yeah, and then your final result will be in terms of u, if I'm not mistaken. So you have to resubstitute back your value of u. Right, so right now let's try solve one in particular question. Let me an example, okay? And I believe that this example I could like use it from a textbook. So give me a second to bring it out. But ironically, talking about Bernoulli, I realized that there are two. Well, one of them is a physicist, and another one is a mathematician. So yeah, well, it's a surprising fact because I assume that both of those names are very similar to one another, but we surprise, surprise, they are both different people and different fields. So anyway, so I found my notes here, and let's solve. Well, I'll be using the example given. So we have here, oops, sorry, dy dx minus 1 over 2 of x, 2x y is equal to 5x square y to the power 5. Now, as you can see here, the value of n, if we refer back to the general form of a Bernoulli's equation, we realize that we can't solve directly by using the integrating factor. Um, Therefore, we have to use well, substitution. And yeah, I had to derive it still. Anyway, so by letting u is equal to y, we know that is raised to the power of 1 minus n, which implies that it will be negative 4. Then by taking the derivative in respect of x, this will be negative 4y. Sorry, not x, dy. Negative 4y raised to power negative 5 dy. Okay. Now, oh yeah, I have to make it in this form. Now you realize that based on this differential equation, we want to get rid of this term. Therefore, by dividing everything or by multiplying everything by y raised to the power negative 5, we will obtain the following, and then we can proceed with the substitution, the proper one. Okay. So from here, yep, as usual, like I showed you before, we complied it, and we will obtain negative 1 over 4 du over dx minus u over 2x is equal to 5. Sorry if my writing is a bit confusing to differentiate between u and 4, but I assure you that the denominator here is u. Okay, so I want this, I want to get rid of that term. Therefore, I multiply both sides with negative 4, and I'll obtain the following, which is plus, well, 2 over x u is equal to 20x squared. Now, as you can see, we could solve this by using the integrating factor method. So we have to obtain the integrating factor. So I will not be deriving it. I mean, I'll make a separate video about how to derive the formula itself. I mean, it's a very interesting one. Anyway, just basically we will be multiplying both sides with a integrating factor. So it will be the following. I mean, generally speaking, that the general form will be dy dx plus p of x y is equal to q of x. And here, to get the integrating factor, you will use this particular formula and we will obtain the following. So this same applies to the differential equation that we are dealing. And then, yeah, solve as usual. We integrate 2 over x dx, and this results will be 2 ln of x, yeah, and then we will obtain e ln x squared by using one of the properties of logarithms, and finally it will be x squared. The reason why we ignore the absolute value is because x squared is always positive for any values, for all values of x in a real set, meaning that we could ignore completely the absolute value. Anyway, this is our integrating factor, which means that we have to multiply both sides with the integrating factor. So x squared d over dx plus 2xu is equal to 20x raised to the power 4. And when you realize this here is the product rule when we take the derivative, it means that it will be like this. X squared u is equal to 20 x raised to the power 4. Now, by integrating both sides, you will obtain the following. X squared times u is equal to we integrate 20x raised to the power 4 dx. And now, solve as usual. So 5x to the power 4 plus c. Dividing both sides with x squared, you obtain 5x to the power of 2 plus cx to the power of negative 2. And there you go. So now you are left with u in terms of x. So you have to go back and find your substitution here, which is y raised to the power negative 4. Y raised to negative 4 is equal to 5x squared plus cx to the power negative 2. I believe that's the answer. Well, I believe. I'm not sure. Oh, forgot to. This is negative, negative, negative. Sorry, when I multiply both sides with negative 4, it should be negative 20x to the power 4, negative, negative. Yeah, negative. Is there anything else I missed? I believe. Oh, sorry. Wow. This is. Wow. Okay. I make more mistakes now. Okay. Wow. I'm sorry. It's already late. Yeah. So this is 3, 4. Oh gosh. 4, 3. I believe that's yeah. Fine. Yeah. So the question here doesn't tell you what kind of solution they wanted, whether it's explicitly or implicitly. Means that if I want explicitly, I have to express y in terms of x. Unlike this one, I'm just leaving it implicitly. So that's how you use it. That's how you use Bernoulli's equation. You identify it's a Bernoulli's equation, and from there you try to convert it to a first order linear differential equation, and then you could solve by previous methods that you have been learning. Okay, so I hope this is helpful enough. And if there's any questions, please do let me know. And if there is any like misconceptions throughout my explanation, please do let me know as well. Okay. And that's all for now. See you later.